today I will just go straight into introduction of Scott Klasky and Norbert Podhorszki from Oak Ridge National Labs that will be providing a lecture on Adios library. Scott, Norbert, the stage is yours.
Okay, thank you so much. I'm going to share my slides. The one thing, if I could beg you guys, ask some questions at different points, as many questions. I give a tremendous amount of presentations, and all I can say is giving so many remotely, it's not great when no one asks questions. So please, please, please ask questions. Now with that, I'll say, I'm going to go sort of according to the script of what we have on the slides, but I want to talk about data first. And here, Norbert picked the title of Exascale, HPC, data management. And the only thing I can say is I work with a lot of, if you want to say, application scientists. And when you think about the commodity that scientists get from computing, it's the data. And from the data, they get the knowledge, which creates their science, which they publish, and they can discover new things. So, everything's about the data. So in terms of like Adios, this is probably at this point not even a complete list of different contributors through the years. So we've been doing this a long time, and it was all based when I was actually a graduate student working in general relativity, and everything I was doing were black hole coalescence. It was all supposed to be to provide, if you want to say, a repository of data that had different signatures for black holes that were computed from the calculation such that when one day, which we never thought would come true, they would actually be able to see gravitational waves. And of course, you guys probably know LIGO and achieved it. So one mistake I made in my life, which was leaving the field thinking that would be an impossible thing. But the fact is, it was all about the data. And, the first thing I'll say is that whenever you look at long-term software projects, and especially one that comes from a laboratory, it's really important to get more people to give you feedback. So, if you guys try Adios, if you have a good experience, if you have a bad experience, I'll say, tell us. We have a GitHub page. You'll see it on almost every slide on the bottom in the center, as well as you can go and email us. Probably Norbert's much more responsive in emails today than I am. But the fact is, we want to hear how we can improve I/O for your code. So this helps us improve Adios, because when we see one having challenges, it's probably a lot of people having challenges. So we call this part of a software co-design process. This is sort of like a exascale computing project that I run with one of my colleagues from Argonne Lab, Ian Foster, which is about co-design for data, for online processing. So anyway, the other thing I'll say is, so we run into, sometimes we get computer scientists and they turn in wonderful collaborators. They modify our code. They give us things back, which then helps the greater community. We work with applied mathematicians. Part of this talk will talk about data reduction. If you want to improve I/O, one way possibly is to reduce your data. The other is, again, we work with so many application scientists. Adios has a unique property that you can actually have a way so that you can create what we call a mini or proxy or skeleton application when you run. There'll be very little overhead. In fact, you won't be able to measure this, but you'll be able to then give the metadata, run this, go through this process, or just give us it. So then we can have a code, a C++ code, which then recreates then the I/O patterns. Now, when we look at extreme scale data management, the challenge that we see is that when you want to work with large data, and this could be high volumes, it can be high, velocity, and you can go on and on with all the V's, what you find is that there's a lot of constraints. Every experimental facility I work with talks about constraints of storage and bandwidth, but there's also the timeliness, which is a major challenge. So that, sometimes when you're running an experiment, and this is the K-STAR experiment in Daejeon, South Korea, and they want to have feedback. They want to know what's going on, especially as we move closer to ITER, which is coming soon. So that near real-time feedback is important. The other thing is, again, that people want their data to be reusable. They want it to be efficient, work well. So our vision is to be able to provide scientists with tools that hide so much of the complexity of the underlying storage system, of the networks. And this allows for efficient data analytics, data reduction, data reuse, movement, visualization, and lifecycle management. So this is a very important thing, and this is part of our driving vision. And as I say, we work with a lot of applications. Some applications like Hank Child, if you know him, he's one of the co-creators of Visit. This is with Visit. There's applied mathematicians. This is with global tomography. So the main authors are global tomography, or seismologists, I should say. So we have papers, and again, one, is with SKA. This was a Gordon Bell nomination. Fusion papers in physics of plasmas, for example, and the list just goes on and on. So the point is that we generally are trying to be helpful, trying to help them solve the problem so that they can get their science done, and they help us push forward. And a lot of times we just start to collaborate further to build and, and to, if you want to say, dream together. So another thing that's important if you're thinking about software sustainability, and we have all the usual things from, nightly testing, continuous integration with over 2,000 tests, all types of reports. We have code coverage. I forget how much of the code is covered, but it's quite a bit. So we really take software engineering seriously, and so much of this is with our commercial partner Kitware. Now, this is just a little bit Oak Ridge-centered view from the ADIOS timeline, and the important point is that we started this back in 2001. This is when, what should I say? There was no multi-core, but there were okay, so the point is, we started with multiple processors on a node, to then moving over to multi-cores, okay, as we kept on evolving, going over to, as this evolved on Jaguar, putting NVIDIA GPUs, over to Titan, over to Summit, and we're in the process of accepting Frontier, and I'm sure, a lot of you guys have heard, it will be the first US exaflop computer, and it will be 1.5 exabytes for the floating point performance. So along the way, we've had to do a lot of things in ADIOS, and at some point, and this was the start of a project, it's a multi-billion-dollar-a-year project called the Exascale Computing Project, where we said we're going to drop everything we did in code, take the algorithms, go from C to C++, and really go further in all the software engineering tests and really get something which is highly optimal on the smallest, meaning workstations, laptops, going over to the biggest computing systems. So we have a lot of I/O challenges, and the point that we usually talk with applications people is, how much do you really want to write? And sometimes that goes beyond just the physical timescales. You're wanting finer coverage that could be for debugging or could be for really understanding deeper structures that may start to exist and could give you a lot of valuable insights. So we want people to write extreme amounts. Extreme amounts means, you know, one of the guys we work with, he was actually trying to write a few years ago 100 petabytes in a week. And we told him the file system is not that large at that time. And that's not going to work because even if you could, it's going to be going from the parallel file system over to dev null, meaning you can't do it. So IO, we needed high performance. We needed to be able to meet the goals so science can occur. And we really need things to be both write optimized, first and foremost, and read optimized. And the general view is that if you write at scale, then the cost, CPU or node hours, is much higher than when you read. And the point also is that you can always go from write optimized to read optimized by reading it once and might not be great into something which is much better. And you can do that with very small amounts of nodes. So we want things to be high performant. We want it to be self-describing. We want it to be good for code coupling so that, again, whether I couple my simulation to some visualization, I don't want to have to go sometimes if I'm doing in situ through files. I just want it transparent. Go through files, whether it's on same nodes or different nodes, shared memory, SHMEM, whatever it is, we want a way to have an abstraction allow for this. And as technology evolves, going over to things like NVMe or going over to these key value stores like a ADIOS solution, we want to make sure we can evolve there. And a lot of work recently has been with NVIDIA and GPU Direct turning into GPU Aware, which we find very important. So we have a high performance publish subscribe system. So when you look at the ADIOS APIs, which we will go over, you'll see it's puts, gets. And we want to have it so that multiple applications can be connected to multiple applications. So think workflow. And if I want to do this, I want it to work well. Or think, hey, I have some experiment, it's just publishing data, and then I can use ADIOS and I could have 5 different collaborating sites all doing different things with this data. So we have a lot of things going, and on this slide, I think it was Norbert who put a list of 4 codes. We have a lot more codes nowadays, which get well over a terabyte per second. So, a terabyte per second on Summit is quite good when it's real code. When we measure, you run the code without IO, you run it with, you make sure what the performance is. And a lot of the numbers often come from the applications people. So for us, IO calls are declarative in nature. So which process writes or reads what? So really, in order to do this, we want to think of things living in a global space. So if you have an MPI code, you can think, hey, I can go, and if I don't really have a traditional global space, I can just say the total number of processors, that's my global space. My rank, that's where it fits in the global space. Or your global space can be from the domain decomposition and where you fit in. You can have holes. You can have multiple processes writing to different spaces. That's all fine through the ADIOS part. The other thing that's important is the strategy is completely separate, from the user code. So whether it does things like creates subfiles, has all these file system hacks, all these things are hidden from the users. The users don't think about it. It's in some of the keywords that when they run, which are supposed to be easy. So this really allows the best method available without modifying the source code. And it allows developers, can create new methods. And when you have a new method, it can be made immediately available to applications. So this was our strategy back, in the early 2000s, and it's one we keep continuing to push. So again, we have self-describing data. What that means is we have a concept of variables. So you think, oh, what's the temperature? What's the pressure? What's the entropy? All those are self-describing. So the way you describe it is you might have variables in your code called P, but in the output, you'll see pressure. So you can put the units by having attributes. This is static information for humans or machines. And they're global and they can be assigned to a variable. So this has always been a challenge for self-describing data to make this high performant. And that's what we keep pushing the envelope to do. So if you want to learn how to use ADIOS to write, here's, I would say, 90-something% of what you need to learn. There is a put. Likewise, there's a get. We have a concept of steps. Okay, so the step can be an iteration or it can be a computational time step or whatever number of that. We have a way to define a variable. Again, this is a variable that will be called temperature in the file. And what this has is it's a 2D quantity which says, what's the global domain? What's the offset, meaning where does that local process live in the global domain? And then how much data does it have? What's the array? So this is how it looks. So you really, again, you don't even need begin step and end step if you don't have them. But if you do, it's highly recommended, especially when you want to go to streaming. But there's a put, and everything really happens on the end step if you have end step. So you can have 20 puts with 20 variables. So again, on the read side, you want to inquire what variable. You may know what the name of the variable is, or you may need to find out this from the self-describing data. And it's very similar again. You acquire like what's the size of the data. We'll have more complete examples when Norbert talks, but this is what gives us very high performance. In this case, we're running a Fusion code. It's very high performance Fusion code. And these are real runs, and this is showing 36 terabytes per second. This is writing to the NVMe, that's node local. And this is another code, GTC, writing to the GPS parallel file system. And this was just showing that we can achieve for this code over 2.3 terabytes per second. Something I talked about the last time I was in Singapore. Python, we have Python bindings. I'm going to let Norbert really go over this, but the point is, again, it's meant to be fairly easy to code and fairly easy to get performance. So I'll just skip over. This is a demonstration of running a code. It's a reaction diffusion equation called Gray-Scott. This is just saying, hey, I can just launch the code, then launch other codes, and you can see other codes are just connecting in memory. This is running on a parallel computer. I could launch things like Visit, and Visit can just connect in memory to the stream. And what you can see as we go through this, you're just getting in situ vids, but every application looks like it was compiled for files. And one of the nice advantages when you do this is that you can go and say, hey, I want to kill off one of these processes. So if I give this a few more seconds, you see we just exit Visit. Simulation still runs. I kill analysis. I kill different processes, but then I can restart them, and then things just can continue. Now, there's different mechanisms to this, but this just saying you're decoupled. What you do is up to you, but it allows just a code that's running that now anyone can connect to if your system allows, or certainly the user can. So let me move on to the next slide. This is work we did for a Gordon Bell Prize with SKA. So there are a lot of participants, and one of the scientists in my group, this is Jason Wang. He used to be in Perth, and one day I gave a talk to ICAR many years ago, and we've been having a good collaboration. This was a Gordon Bell Prize nomination last year. And again, what it will say is that we can actually get really good parallel I/O performance for the full SKA pipeline on Summit. This is actually showing we can get 925 gigabytes per second in 512 nodes, which is, again, quite good. And again, 99% of Summit was able to generate 27,260 channels in 2 times the real time. Now, rather than saying it, we have a video of Andreas.
Hello, everybody.
Hope you can
In
hear
this
it.
short presentation, I will show how we've integrated ADIOS II to enable SK scale
Yep, it's
processing
soft, but we can hear it, Scott.
via Switzernet, and I'm presenting on behalf of the ICRA Data Intensive Astronomy team and the Gordon Bell Prize finalist team. ICRA is the international.
So rather than give this video, which I'm sure many of you know, Andreas, I mean, the point we're all talk about is similar about how they've been upgrading to ADIOS II. They've been working with our team, and they've been getting some amazing results. So we want to keep having further relationships with Andreas and with more applications around the world. So this is another application. It's a standard benchmark code on many high-performance computers. It may not be for yours. It's called GTC. It's written by a good friend of mine, Zihong Lin, who's a professor in physics at UC Irvine. And one of the things that we saw was that, you know, the way that they've had their code was using netcdf. And if you look at the time it takes in a run, this is the time in seconds, you can see I/O is one of the most expensive things in the code. And what that does is it really gets them to say, okay, we can't write that much. But, you know, we talked about getting ADIOS integrated. We got a time from 12,880 seconds to 606 seconds. That's a nice performance difference if you see. So that now I/O is not the bottleneck, and now they can write a lot more often and no problem. And this is the kind of thing that we talk about. Now, if I go further, and
this is what reason ADIOS team that help GTC, and I borrowed one slide from Scott's group to highlight this. So the GTC code has been selected to perform the 2022 theory performance target by DOE to predict the alpha particle confinement in ether burning plasma. That requires thousands of times more computational resource than the example I show for the D3D simulations. So by enabling GTC with the ADIO framework, we can finally write out all the majority of particle data with minimum impact to the code performance. And as shown by Scott's group, GTC generate large number of data, and the optimized ADIO on GTC were able to reach almost the peak performance of over 2 terabytes per second. And those performance was done by a new engine inside the ADIO, which was developed.
So I'll continue. And again, if you kind of get the theme in the start of this, I like when other like high-level scientists talk about our work versus I'm always talking about our work. So I think it's really important to illustrate to people who don't know us that we have all these cases. This is a code. Has anyone heard of SPEC FEM 3D Globe? It's a very common code for global tomography, and either everyone's quiet or no one's heard of it. The point is that we've done, we've worked, we've co-designed with them, and this is a code which really needs to, it does a very complex workflow. And what happened is that in their workflow, they need to be able to write out 7.5 petabytes of data in a single workflow step, which is a lot. So they had to have very efficient I/O. And we did, a tremendous amount of work with them to make sure that we can reduce that time and think of 150 seconds to be able to write their data for one of their big runs. So they've written their geophysical journal. In this case, they include Norbert on this.
1,000 earthquakes. It's about two.
This is one of their key postdocs, Wenji Li.
Petabytes of files we have to dump into the file system and then be read back into the agent simulations. So some performance metric about ADIOS on Summit. So we finished a few different kind of tests. The first one is stress test. So we perform about 50 earthquakes. It takes about 80% of the Summit computing power. And in total, it dumps about 250 terabytes of files into the file system. And we compile different methods for the ADIOS I version. So you can see the POSIX and MPI grid give similar performance. And then recently we just migrate to ADIOS II. And we also did test using the BP3 and BP4 as backend engine. And you can see there's still quite a lot of improvements given we migrate from version 1 to ADIOS version 2. And the last one is some metric about, a performance metric of the real production case on Summit. So currently for a most recent model, we have about 2,000 earthquakes. Each earthquake will generate 1 terabyte of wave field snapshots. And in total, it will dump more than 2 petabytes of wave field snapshots into disk. The total simulation will use about 2,560 Summit nodes, more than 50% of the power. And the total running time for the forward simulation is about 3.45 hours. This step includes the saving all the snapshots to disk. And I/O based on measurements takes about 25% to 30% of the overall running time in forward calculation. And in the agent simulation, which is essentially backward calculation, the total computation takes about 4.5 hours, but this step only involves reading the snapshots. It's kind of less demanding as the last step, which we dump the files. So I think overall, we achieved great performance of ADIOS. Our collaboration with the ADIOS team started from a long time ago. I mean, the time when we used Titan. And then on Summit, we continue using the improvements, making improvements on the softwares. And this is the performance metric you can see. And I think overall, ADIOS really help us to save our I/O time.
Okay. So when we think about ADIOS, there's so much work that we do with data streaming. So, we have high performance data streaming for this PubSub environment. And, we started out where, this was all about you run one thing on one node, one thing on the other. And we really looked at this mathematical weak coupling. We then started to get all these demands to go to mathematical strong coupling. We've done optimizations, and we allow for so much more. So we have a method, it's called SST. And what this does, it allows one producer to have multiple handful of readers, and they can come and go. And that was similar to the first video. And it can use TCP or UDP and RDMA. So to get the highest performance, of course, it uses RDMA, and underneath it uses libfabric. But other methods have, other technology. So we have these engines. One is written by, again, Jason, the guy who was in Perth. He developed a Adios Engine, which does, it does one-sided MPI communication. So SSC works. It gets some higher performance better than SST, but because it's MPI, you can't have applications come and go. So for some things like visualization, you want to be SST, and for code-to-code coupling, where if anything dies, it kills everything, you can go to SSC. And then we have, by our kitware colleagues, they developed a way to work directly in line, and that allows codes to use memory references. We also have a technique called DataMan. Again, this was developed by Jason, and this allows wide area network, and we can show wide area network performance. So when we look at this and what's going on, we see that we can achieve very high performance. I'm going to go on and say this allows for high performance for code coupling. So ADIOS is used in the whole device modeling. This is the Fusion ECP project. It allows, again, so that the total time that the large simulation, the one taking 90% of the resources, the wait time compared to wall clock time is down to 10 to minus 6. So we can have strong coupling, and it's not like it slows down the calculation. And what's nice, again, is that things can also run in an asynchronous fashion.
How is ADIOS
I'm going to
being
skip
used
some of the video in the sake of time. The point is that we're pushing forward, and as we push forward, this is actually showing some of the work we've done with K-Star. And what this really has done is allows then from this remote instrument to use ADIOS. It goes from Korea to the US, and that we've turned something which goes from 12 hours to 10 minutes. So we allow the data actually be streamed in. And one of the things we want to do is, of course, accelerate this. One easy way is to make a GPU enabled versus this was some of the Intel 5s. So we're now modifying the workflow, and eventually, of course, latency will be an issue. It's 150 something milliseconds, and the data that's generated is from a camera that is a megahertz camera. So we have to get the right mix for latency and bandwidth, and then getting it into the workflow. This is a video. Again,
Okay,
I'm gonna skip it for the sake of time to say we also work with cancer and projects. This is actually looking at, I believe, COVID. This was this was part of 2 years ago, a Gordon Bell nomination. And one of the big things that we did was we allowed the process to be asynchronous. So I'll let the scientists here talk.
In a very short while, I'm going to explain what we are trying to do with Deep Drive MD, which is an approach towards getting 100 times faster per simulation performance for complex biological phenomena. So we study protein folding, we study disordered proteins. These are all fairly large systems on which we are trying to do work. And that's actually driven by this motives that you actually have adaptive ensembles that run all the time. So you saw massive simulations in the previous applications. Here we are actually running like optimized simulations on single GPUs, but the data that it is outputting is quite large that needs to be collected, and we need to run some machine learning models on top of them. It's not just one model, but it can be an ensemble of models. It can be different models that are running at different time points and so on. And then you can really think of it as having two phases. One is a learning phase, other one is the inference phase. So in some sense, this is a streaming application of machine learning and AI methods that eventually allow us to like run as the simulations are running. You learn and you make decisions on the fly to basically say, should I start more simulations or should I continue with the same ones? Of course, the machine learning framework is supported using the Candle infrastructure, which is another ECP project, collaboration with the Shantanu team. And of course, many of these things are very helpful. And does it really help in the real world? Yes, if you were to implement this using just the file system and so on, we can actually see quite a bit of improvement in terms of the sampling. So here are plots that show the absolute timescales in microseconds of that is the amount of simulations that were done. And we look at the explode population of states that were sampled. And it's interesting to see that the Anton trajectories, which take about several microseconds to actually identify the folded state, we can see the same thing within a couple of 100 nanoseconds, which is kind of cool because you are now able to get at least 1 order of magnitude speed up just because you're using a machine learning driven approach to do this. So we showed that this worked in a previous approach. And so this is good, but now we need to take it to a higher state. So ADIOS is actually something that enables us to run these enhanced scalability, especially in the context of streaming AI. And the way we do that is by implementing ADIOS MDS, which allows us to stream the MD simulation data continuously within the context of this learning loop that I just spoke to you about in the previous slide. And the streaming application of ML and AI is kind of running all the time. So there is it's running as if it's an infinite loop and the decisions are made online as the model learns. And we are constantly training or retraining and then allowing the model to evolve over time. So with respect to a file system implementation, we can sort of compare the sorts of benefits we get. Yes, of course, in terms of the sample states, we see the same amount of benefits. We can actually increase the order of magnitude acceleration by about 100 times. And the resource utilization is something where ADIOS actually helps us a lot, which is that you can actually see that many of the resources that are being used, they're not idle as compared to the system-based implementation, where many of the resources are actually spending time waiting for data to come in or waiting for more data to be generated and so on. So this enables us to get a faster time to solution from the streaming runs. And where we are enabling that is essentially trying to take it towards more of these extra hardware that is coming. So AI hardware has become a huge thing. And we can actually train on very large batch sets, especially with something like Cerebras CS1, where you can get nearly 20x times the large batch sizes we really care about. And this effective use of these hardware under continuous resource runs and so on is important. And that enables us to get at least 500 orders of, 500x performance gain in terms of, sampling.
Let me continue. I was told there's questions, and of course, when I try to click and read, it stops the video. So I apologize for that. Great feature of this. I was asked, I think there's a question that Norbert said I would answer about, what was it? The multi-tiered storage, is that correct?
Yes, so that was my question about the support for multi-tiered storage and data staging on various technologies that you can have within a supercomputer environment.
So I want to get to that slide. I'm probably going to be skipping some slides to make the talk, which I say try to fit in the time. So multi-tiered storage, there's a lot of ways we do this, and this can be a very deep question. On the very essence of this, we can write to all different forms of NVMe as well as different storage tiers. And that's why essentially on the systems that we work with, it's a directory change. And the way that the BP file format works, it will all work the same. The biggest thing is like, where is that metadata if it's writing to no local memory? But we have this, it's implemented. But the deeper part of this is what I'll get into very quickly when I get a reduction. So if I don't get an answer that, let me know. So I will get into that. This is just some examples, again, of things that we've been doing as we've been getting integration further and further into AI and trying to really understand where the bottlenecks are. And a lot of this, again, this is working with a cancer application. It's called QUIP. Just a few more points. So, there was a question about multi-tiered storage. But the real thing, and, so I was on the executive committee, and we're actually submitting a report, a journal paper about the workshop. But it's all about reduction, and if you want to say compression, reduction. And the real thing, and I'll just get into this whole point. So how does this thing happen? So when we talk where we're going, I'll just put it like this. We're trying to have a way, and I'm just trying to get to the right and this is the right thing. We're having a way so that, you know, when data is written, think of it as that you write it in a contiguous way. The way that you give the data is the way it's written. But what if you could refactor the data or have these techniques which can really say there's the really important pieces. This will give you a certain level of accuracy. As you go down to the lower tiers, you'll gain more and more accuracy. So the point is that what it does is allows you to say, here's the original data, but if you wanted to read, if you put this top piece, which will be tiny in comparison to the full data, put that in the upper storage tier. You can visualize and you can see that you can get a decent visualization, know what's going on. The error, again, red means that it's getting higher. The error is pretty high, but if I was actually having every data point, which we call degrees of freedom, then it would be, this image would look completely black. So there's certain points, more probably where you have certain artifacts that the algorithm found important. This algorithm is based upon wavelets and multi-grid. So it does these, what we call L2 projections. I don't want to get so much into the mathematics, but what it allows you to do is to say, there's a realization that what you want to do is have a metadata file and then manage that from the fast storage tiers, which don't have much storage, and manage down to the lower tiers. So this is a research project that we have, but it's one that is important in that, you know, it allows us to now place on the different storage tiers and allows us to then really think how we can use multi-tiered storage effectively. So this is a major activity. There's still fundamental mathematics that we're working with, but we're actually trying to get designs. This software MGuard, you know, we're going after an R&D 100, and it has different properties. And the main thing, again, is that what it does is it just goes into the data that you're transforming, creates what you can call residuals, or these coefficients, creates a hierarchy of this, and then after it does that, then it can do the other common things, which is go through a quantization and compression step of that. And it will do this, and you'll know what error, so you can know how many levels of your hierarchy. So we had a recent paper actually at Supercomputing of this year, which described this, and the storage hierarchy for us, as it is for many other scientists, is the lowest tier is tape, because that's where you can store things really long term. So there's tape, a parallel file system, and then, you know, the NVMe. So we're trying to manage across multiple tiers. And ADIOS has the mechanism and a file format, which actually makes it quite easy to do, because not everything is lumped into a file. So we have this separation. I don't know if that answered the question. I can see the chat window when I'm playing videos, so you can let me know. So again, MGuard has, it's a mathematical theory turned into software, and it really tries to be able to mathematically prove that your data, and not just your data, but data in derived quantities, one that we call quantities of interest, that the errors in the quantities of interest can be conserved. I'll just get into this a little bit, and it just basically looks and says how this happens. And it's kind of nice because it works with these complex meshes. It really works with non-uniform meshes. It's a bit challenging right now, and certainly not one we would just give to people for unstructured meshes, but that's, you know, further and further where we go. And we've had papers on it, but getting it in general software is hard. But it really tries to make sure, in this case, that if you're reducing this quantity, in this case, it's a 5-dimensional probability distribution function, and it wants to then try to make sure it can preserve these complex quantities of interest, from density to temperature, the parallel temperature, the perpendicular temperature, and it can do a good job preserving that. And again, right now we can do linear quantities of interest. So with that, being a driver for how ADIOS works for multi-tiered storage. And this is actually showing how we're using this with climate data coming from the US E3SM code, and just showing that we can reduce the data. So in both these cases, we're showing that we can reduce the data beyond what they do by, in the one case, a factor of 77. In this case, actually what they're happy with is a compression ratio of 24x. The other thing with I/O is that as you want to keep making it faster and faster, you would like to be able to do some form of compression to write less. And the thing that really saves us is GPUs, and it saves every compressor out there. So we've always tried to use different compressors. GPU is the real thing that makes it, this is showing on Summit the theoretical bandwidth per node, and we're significantly faster. So this is now really transforming how we actually think about I/O with reduction. So this was a video, but because of the sake of time, I will not play it. And at that point, I'll leave Norbert. Is there some final questions that?
Yeah, well, my question was about integration with accelerators and what happens with ADIOS. I know it's doing a very good job when you do data streaming in the CPU, but what happens when you add the accelerators in the mix, whether it's NVIDIA or others, and basically a multi-memory tiers. So when you have to move buffers from CPU to GPU, and how is that dealing with that portion? And more specifically, as you probably know, we're doing a lot of work on NVIDIA GPU direct storage that allows you to get the data from the NIC straight into the GPU. So how is ADIOS handling that? And as Norbert mentioned, I know that there is some work being done by my colleague CJ in the US and your team, but I wanted to hear from your side, how is ADIOS planning to move forward with this integration?
So so before Norbert goes, maybe it just so happens that, for the fun of it, we have another review. This is a review for ADIOS project. So if I could just share a slide, and since Norbert's going to be talking in a bit.
This was my first answer. So in the ECP program, GPU aware is a functionality that is very interesting, and so they decided to give us extra money to pursue this and develop this for the upcoming big machines. GPU aware means that the applications having data in the GPU, right now there have to be multiple steps to copy that data out from the GPU into the CPU by the application, reorganize it, and then call ADIOS, which will buffer it and make another copy. So GPU aware would mean that ADIOS can get a GPU pointer, and then it will download from the GPU to the CPU memory when it fits for the I/O, and then it will output it. And it's reducing the number of copies. And so the results that Scott was trying to show was about showing how that performs better. This is basically driven by some ECP applications who has lots of data on the GPU. So that's the whole ECP is behind that idea. And then NVIDIA's GPU Direct is a specific technology to NVIDIA's, and we don't have projects, only collaborations, research collaborations of trying this out and making a prototype of it. So
Can you use reduced results as checkpoints for restarting numerical simulations?
Okay. I'm trying to answer this in a good way. This is if you do lossless, of course, okay. If you do lossy, there's so much that people care about for both accuracy, which you probably can, of course you can do, because again, you just give a high error bound. The challenge that everyone faces is numerical instabilities, which can appear. So it's really not even like a code by code basis, but it's even sometimes what you're running, some of it, the instability won't appear, other times it will appear. So, you know, people have published saying you can, but I would still say if you understand the mathematics enough, you're crazy. Now, here's the thing. If you write a checkpoint and it's written, but then the system can become consistent, self-consistent again, then you can. So it really, you know, up to this. But if you're saying, can I do that every time step and then read back from the time step? So write the checkpoint with a compressor, lossy, read it back, compute, do that for every time step. That's where all the instability. So depending upon the frequency, depending upon what could happen in the mode structure, if your system will not self-heal, you can add dissipation. All these things can affect. So I would say no one really should do that. I mean, until the mathematics is completely worked out and no one's done it, I would say no, don't. Sorry.
Okay, thank you.
So the plan would be save compressed and save your checkpoints apart.
I mean, I'll say it like this. How often though do you write your checkpoint? I mean, on Summit, the largest users we know are generating, I'm trying to remember, it's like 100 and something terabytes. They write it once every hour, the most frequent, and we're getting 1 to 2 terabytes per second. So every hour you're taking 100 and something seconds. No one cares. And to jeopardize the potential use. Now, if you're saying checkpoint, but you mean for analysis, that's a different story. Then of course we can do that. But it really depends upon what we call the quantity of interest. And that, again, do you know the majority of the terms that you would derive? So we're working with Climate on this as well, because again, it's gain trust. So our whole point is, what if you can write it and have these tiers so that you can get really high accuracy, but when you read it, now you can do this. Imagine now you can, when you transfer data, you can transfer the higher levels of the hierarchy to a certain, give you a certain error. And if it's large, you may not have time to transfer all of it. So there's a lot of things that you can do when you think about this progressiveness.